In this video we are going to introduce and give some examples of deadlock. What I need you to recall for this video is the basic idea of concurrency, particularly mutual exclusion as a concept that we need to enforce when we're talking about resources. As a quick refresh from the definitions we gave last week, we defined a deadlock as a situation in which we have two or more processes and that when they are unable to proceed because they're each waiting for the other to do something. So there are many and varied ways in which concurrency can result in deadlock, but we are going to talk about in these videos the most common cause, which is competition for shared resources. So in this case we're going to discuss a situation which has the potential for deadlock, and that is a four-way intersection. So we're not actually going to introduce processes, we're going to start with a real-world example. Let's imagine that we have a four-way intersection here. A vehicle approaching from the south has to progress through two quadrants of the intersection and needs both of those quadrants available in order to proceed. It has to occupy both quadrant A and quadrant B. At this point, we have no potential for deadlock. We can have as many processes proceeding down this lane, or as many cars proceeding down this lane as we want. We'll never end up with any sort of deadlock. Another car approaching from the east requires access to a different pair of quadrants, B and C. Again, in this instance, we have no problem with deadlock, because even if car 1 takes resource A and car 2 takes the second quadrant, car 1 will be blocked. However, at this point, car 2 can simply take the final resource it needs and exit, leaving car 1 able to carry on its way. So we don't have a possibility for deadlock just yet. A third car entering the intersection still doesn't create the cause for deadlock, because there is nothing actually preventing car 3 from operating through its lane if it needs to. So again, we can have cars being blocked by each other whilst trying to access resources, but there will always be a way in this scenario where one car can move on, free up its resources, and the other cars can continue. However, once a fourth car enters the mix, we have the potential for deadlock. At this point, there is no deadlock itself, because in theory, car 1 could progress through its lane, leaving the situation unblocked, and then we would reduce ourselves back to a previous situation of having 3 cars and no possible deadlock. So at this point, we have what we call a potential deadlock, but we don't have actual deadlock yet. A situation of actual deadlock occurs when all 4 cars attempt to grab their first resource before any other car can access its second resource. So in this case, each car moves into the first quadrant that they need from the intersection, and we have all 4 cars, having access to their first required resource, whilst all require a resource that is currently being held by another car. So we can see very clearly here, unless we have a car move back out of the intersection, i.e. releasing a resource, there is no way for any of the processes to continue, and this is what we call actual deadlock. So now we have a feel for the idea of deadlock and the difference between potential and actual deadlock. We're going to discuss 2 very similar examples where one has the potential for deadlock and the other has no potential for deadlock, and we're going to introduce a diagram called the joint process diagram, or JPD for short. And we're going to see how that diagram allows us to see that there is potential for deadlock in the first scenario, but no potential for deadlock in the second scenario. So the example is that we have 2 processes, each of which require the same 2 shared resources. So we have process P and process Q, and they each require resource A and resource B to do something. In the first example, both processes attempt to get both resources before continuing on with their processing. They just do it in slightly different order. So process P gets resource A, then B, and process Q gets resource B and then A, and then releases them in the same order. Intuitively, we can see that mechanism for deadlock in this example over here is the same as it was with our four-way intersection. Each process can proceed and acquire the first of two resources that they need, thereby blocking the other process from acquiring their second, giving us the deadlock situation. What we have over here on the left is what we call a joint process diagram. So this is a diagram where we can represent two processes and their execution along with possible paths of multi-threaded execution and also requirements for joint resources. So we are representing the progress of process P here on the left, on the x-axis, and the progress of process Q on the y-axis. And in the black lines represent different possible ways of executing one or the other processes. So all of these lines move at right angles and they represent a certain progress through each of the processes. So whenever one of the black lines is moving from left to right, as is in the start here, that indicates that process P is progressing, whilst when the lines move vertically, that indicates process Q progressing. So the simple example we can see is if we follow the line 6, so that from this point here, it indicates process P and then Q and then P executing a little bit, but this is all before our get A and get B, which are the first instructions that we have listed in process P and Q. So in this line, we have process P progressing up till it gets resource A, and then progressing and continuing, we're looking at line 6 here, up until it gets lock B, progressing again up until it releases its hold on resource A, and then proceeding on here. Whereas in line 5, what we have is, I'll represent this with green, what we have with line 5 is the same progression up till getting lock B, process B, but then Q starts executing. However, at this point, Q requires access to resource B, which means that it will be blocked, and the only possible execution here is the continuation of the execution of process B up until it releases B, at which point process Q can continue. Now the main thing we care about on this slide here is the representation of requirement for the shared resources. So what we've got on little arrows here on the Y and X axis here are indicating sections where that particular process requires that particular resource. So between the get and release A sections, process Q requires resource A. So that corresponds to this section here. So what we can see is that for resource A, which is red, we have an overlapping area where P and Q both want resource A. We also have, for resource B, an equivalent overlapping area where both P and Q want resource B. We can see the inevitability of deadlock in the case of progression lines 3 and 4, where each process can proceed up and into a region of the graph where there is no way for either process to continue executing without entering a region where both processes require both the same resource. So there's no possibility of continuing execution to get out of this region. I encourage you to pause here on this slide and look a little bit more carefully at this diagram here and see that world line 3 and world line 4, the progression line 3 and 4 correspond to the cases where we get one resource for each of the processes, thereby blocking the other. And we can see how this shows us the fact that it's impossible to avoid deadlock in this scenario. So a slight modification to the same situation is if we leave process Q exactly as it was, but we change process P so that it only asks for one resource at a time. So it might have been that process P needed resource A and resource B, but it didn't actually need to hold on to both of them at the same time. It could do whatever it needed with resource A, and it could do whatever it needed with resource B separately. So we'll look at the joint process diagram for this and see why this does not result in deadlock. And we can see intuitively how if we go through any possible paths, interleaved paths through these two processes, how there's no way for us to end up in a situation where one process can't at least continue going on. So the joint process diagram here shows regions, again, where resource A and resource B are both required by the same process. So process P requires resource A for this region here, and resource B for this region here. While process Q still requires overlapping sections for its resources. So it first requires resource B, but before it releases resource B, it still requires access to resource A. And so we end up with these overlapping regions where both processes require the same resource. But what we have is we now have, through any possible path line of processing, even if we end up in a certain region here where the future might involve a conflict over resources, there is still a path of execution possible. So our lines 3 and 4 still allow us to progress through and past the area of contention. So we no longer have a section where there is potential deadlock. Because let's say we look at path 4. Path 4, if I will denote it in orange, involves process P getting to the point of requesting resource A, executing for a little while and then being interrupted, allowing process 2 to proceed up to a certain point, and it will proceed up and acquire its resource B. At this point, it could be interrupted, allowing process P to continue executing, at which point it gets through and releases resource A. So now, even though process Q has resource B, process A may try to access it and be blocked, but process Q can now proceed through and acquire resource A, because it's no longer held by process P, and then continuing executing, eventually releasing resource B, which will allow process P to get and release B before process Q continues on, eventually releasing resource A as well. So in this video, the main thing that you need to have grasped is the intuition of what deadlock is, and the difference between having a scenario which has the potential for deadlock and the actual case of deadlock itself, when we're already locked and nothing can continue on. We've also introduced the joint process diagram as a tool for helping us look at scenarios involving two processes and examining whether or not deadlock is possible. But you can obviously yourself see that if we tried to extend that into more processes, the joint process diagram would not be particularly useful.